Alright, so hi everybody, I'm Dan. Some of y'all know me, some of y'all don't. I'm going to talk to you a little bit today about going serverless. So in traditional stacks, what everybody's used to is we have to deal with standing servers all the time. You have to deal with configurations, deployments, management, and continuing maintenance going on. Well, in the serverless architecture that we're going to go over today, we get rid of a lot of those problems and we get to focus on functionality. So first off, what is serverless? Serverless is essentially just an abstraction layer for the machines and services that run your logic. Now the key there is running your logic, not necessarily just your code, but your logic. So think about the way that you design your code a little differently. We're not going to try and design a large-scale API. We're going to design functions. Those functions are going to handle what we need to do in our code. So we're going to do functions as a service plus. So what does serverless do differently? Well, serverless starts off by enforcing a microservice paradigm, and that's going to change the way that you're designing your applications. It's going to reduce your overall complexity, and it's going to give you better encapsulation of concern. You're going to simplify your deployments by not having to build giant architectures with 30 servers and scaling configs, and having to worry about how that's going to scale up or scale down based on your usage patterns. You're also going to reduce your administrative burden. So the amount of time it takes for you to actually manage those servers is going to go to next to zero because there aren't any standing servers. You also have a framework that's highly extensible and has built-in scalability. So if we're moving to an event-driven microservices architecture, what does that actually mean? Well, what that means is we're going to change the way our entry points work for our application. Instead of having a client that connects to an API, that connects to a machine, that runs a particular code path, that returns you a particular type of result, we're going to split out our concerns into little chunks. Each of those little chunks is only going to be responsible for a handful of things. So if we want to make an API call or an API endpoint that handles user management, well, what kind of stuff are we normally going to create? We're going to have a user create function. We're going to have user update functions. We're going to have user delete functions. And we may have other functions like being able to add on a profile image or being able to send an email. Well, all of those things we can encapsulate better. Instead of running in one large API, we're going to design those as functions. When we design them as functions, we allow them to be independent from each other. They operate without overlapping. We can keep our dependency management a lot easier, so any of the libraries that are required, we can minimize to just what's necessary for that function. So if I'm going to create a user account, I don't need to have email capability in that particular function. There's no point. So why do we include it? We don't really need to. But traditional architectures would make sure that you actually have to. Using this, we do not. We increase application availability since the modules are isolated from each other. So what that means is if we have a particular service go down or subsector of a service go down, the others are not affected. So if we have a particular service for emailing users as they sign up, if that email function dies for whatever reason, we can still create users. It doesn't mean that one piece of the system is going to stop all the other pieces of the system. They all operate independently. When we use this type of architecture, it's very easy to integrate with multiple event sources as our entry points to drive complex workflows. So what does that mean? Well, in traditional architectures, let's say we create a user account. That user account needs to trigger off an email to the user who just signed up. It needs to trigger off creation of role assignments for permissions. It needs to send off an email to an administrator. It may need to even set up a dashboard for that user that requires database records. Well, instead of having all that logic contained in one API call that has to be very complex with lots of edge cases and error handling, why don't we make those individual functions? If each of those functions operates independently, then we know that if any of those fail along the way, the whole process didn't fail, just that one piece. When we're using an event-driven microservice architecture, it also gives us a lot of flexibility. The flexibility allows us to use different types of events to trigger functionality relatively easily. So this is a very simple example here where we have a client who's going to try and create a user account And on that user account, it's going to trigger an email. So the client is going to, from their smartphone, perhaps through an app or on a website, sign up, create a user. That's going to go through our user post call, which is the one on the top. That's going to hit our event system, and that's going to trigger an email. It's automatic. If the email goes down, that's not going to affect our user sign up. If the user sign up goes down, the email are still fully functional if we have other servers that are still running, or other serverless architectures that are still running that can utilize that function. So when each of these is encapsulated by itself, we could have 3, 4, 5 different stacks that are actually all utilizing the same email function. And if the user post function dies, everything still functions except for that one piece. Same thing is true for things like a profile post. So let's say we want to add an image or update a status, and there's an image included with that. We're going to upload that image, and that's going to go to an S3 bucket. But we can trigger off of that event without having to write logic manually to perform this action. We can automatically say, hey, a new image was created and dumped into this bucket. Go ahead and execute the format image function and create 15 different sizes of it for every possible device. Put those right back in the bucket, and now you immediately have logic triggering logic, triggering logic, which allows you to not have to write all that manually. So you're talking thousands of lines of code that you can do with just events, and you don't have to do much setup at all. We can also do things like time-based events through CloudWatch triggers, which allow us to do schedules, cron-based style schedules, to trigger nightly functionality, hourly functionality, even millisecond-based functionality for anything that has to happen quite frequently. So for example, if we want to say we're going to create 1,000 users today, and at the end of the day, we want to be able to have an export of all the users that were created, we can do that, and relatively simply. We don't have to have a standing machine running that cron job. We don't have to have anything maintaining our schedule at all. In fact, CloudWatch will maintain your schedule for you and trigger your function with the proper event, and then you just get to worry about your logic. What do we want to export, and where do we want to put it? So it maintains separation of concern and significantly simplifies your code base. Deployments. So I'm sure everybody here at some point has done a traditional stack deployment, or at least part of one, or been involved in one. And you may or may not have had to deal with pumping out 20 or 30 servers, or even just 2 or 3. Every time you have to stand up a server, it always takes time. It takes time to spin up a server. It takes time to get it configured. It takes time to get it added to a load balancer if you have to do that. It takes time to get security set up. Well, why do we want to deal with all that? We don't need to. What we care about is our functionality. Functionality is what we're selling to the customer. So if we're using a microservices architecture using serverless, our deployments are extremely simplified. We're just deploying functions. We're not deploying machines. So in essence, we're just pushing up a workflow. So to do that, we're going to use individual functions. Each of those functions is self-contained. We can deploy those as a service, which means we're going to deploy all of our functions at once. Or we can deploy one function at a time. Let's say we need to make an update to our user function that decides, hey, we're going to append or prepend characters to their username based on the requirements for our system. That's relatively easy to do, and you can update just that user function. You don't have to update your entire service. It makes it incredibly simple to push out very small, frequent updates, which allow you to keep high code availability, and you're constantly on your game. You're never falling behind. When you're doing this, it's also relatively simple to do cross-account deployments, which makes things a lot simpler when you're delivering code. So an example of that is in a recent project that we had for H3, all of the original architecture was running on my own AWS account, the entire thing. All running serverless, and to deploy that to the customer account, all we needed was one role assignment to my account that grants me access to publish to theirs. After that, all I do is export which account I'm using, export the deployment command, the entire stack is now deployed on their account, completely separate of my own stack. So in a matter of minutes, we can deploy duplicate environments across multiple accounts. It's easy to manage, and there's no longer this massive headache of figuring out, okay, well, I've got server keys I have to worry about, I've got to authenticate into a particular database and update rows here. This makes it way, way, way simpler. If you're going to tear down an environment and you have to kill servers and shut things down and back up files, you don't need to do that anymore. The stack is fairly automated. If we want to tear it down, just tell it to tear it down. All the resources disappear. Buckets go away, files go away, functions go away, API services go away. And for packaging concerns, you have completely customizable packaging for every individual function within a service. So if you want to say the create user function only needs 2 libraries and that's it, that's fine. Just include the 2 libraries in that function call during packaging. If you want to say it includes 45 shared libraries across all of our service, you can do that too. It makes it fairly simple to contain all of your dependencies. Execution cost. In traditional deployments, everybody's familiar with a server stack where you have to figure out how much is it going to cost me to run this server. Well, it may cost you $1 an hour, it may cost you $50 an hour. It depends upon what you're running. You know, if you run a big server, it's going to cost you more. You run a small server, it's going to cost you less. You always have to run into issues with that, though, if you have to deal with scaling. How do I determine costing with scale? That's hard. Well, in the serverless model, you don't have to worry about it. Everything scales on its own. So functions scale based on need. There's no server that has to be scaled. When you do that, you're also not paying for provisioned server when it's not needed. So if your code's not running, you're not paying, which is a great thing when you're talking about potentially thousands of dollars a month in wasted server cost. Cost scales as your application scales. So the more people that are using it, the more calls that are being made, the more it's going to cost you. If you only pay for the execution time used, you're automatically gaining money back every time that call stops executing. One thing that you need to pay attention to, which is a slight caveat here, is you don't want your code running when it's not needed. So don't let your code do arbitrary processes for no reason. Design your functions to do one thing or 2 things, very small, and have it die as soon as it's done. You don't need it to live anymore. When you execute locally, you're going to pay nothing. So your development environment on your local machine will cost you $0, which means you can do your entire application testing locally and pay nothing, and just deploy when you're ready. Administration. You don't need to monitor servers constantly, which if anybody here has had to do that, it's a pain. Trying to keep servers alive, figure out how many connections are on it. Are your connection pools draining? Are you running through your bandwidth too fast? What about your disk usage? What about your memory usage? Is all of that scaling properly, or is it not? When you're administering this way, you don't have to worry about that. So goodbye Nagios, if anybody's familiar with Nagios. Older enterprise monitoring tool. Functions can self-report through properly configured service alarms, allowing for proactive support. So if a server goes down, traditionally you'd have to have something like Nagios configured to constantly ping your servers. It's saying, hey, are you alive? Are you alive? Are you alive? Are you responding to requests? Are you responding to requests? The problem with that is it's only somewhat proactive. So if a server dies, it may be 30 seconds, it may be a minute, it may even be 30 minutes, depending upon your configuration, before you actually know that that server is not functioning anymore. You may not know immediately. Well, if you're in a production environment, you've got critical, sensitive data, you need to know now, within seconds or less. If you're using service alarms on your functions, you can tell when your functions are not running correctly. If they ever throw an error, you can immediately be alerted. You can be alerted 50 different ways. You can be emailed, you can be phone called, you can have messages sent to your phone. You can have all kinds of different alerting mechanisms based on a whole variety of metrics for your functions. If you expect a function to execute 50,000 times every hour, non-stop, if it ever falls below 4990, you can have it trigger off an alert. If it ever throws an error, you can have it trigger off an alert. If something's not supposed to run, and it does, you can have it trigger off an alert. So it's highly customizable for you to be able to figure out however you want to be alerted for any possible scenario, you can do that. In a traditional scaling system, you have to worry about setting up load balancers and scaling configs. You may end up having to deal with configurations on each individual server. You may, or almost certainly, will have to create a server image for your base image, which is what's going to be deployed out for each server as scaling happens. So let's say we have one smartphone connected to the system, performing one API call. You've got one server running, no problem. What happens if you have 50,000 clients executing that API call? Well, now you're going to have to spin up 30 more servers simultaneously from one AMI that has one base config. What happens if your base config is incorrect? Your whole thing goes down. Nothing functions anymore. If you're using a different architecture or going serverless here, you don't have to worry about scaling the traditional way with load balancers and configurations and servers and scaling policies. Everything scales automatically at the function level. So we don't have to configure a server. We don't have to configure a load balancer to determine what our policies are. If you hit 20,000 requests, you don't have to say, how many servers do I need to handle 20,000 requests? What's the average payload size for any of those requests? Am I talking 2K? Am I talking 50 meg? That's going to affect what your scaling policy is. If you're doing it this way, you don't have to worry about it. It scales on its own. You literally don't do a thing. There are a few cases outside of the function level where you have to apply scaling policies at a database level, but from the logic standpoint, you literally do nothing. It scales on its own. Caveats. There are some. Know your cloud provider. Resource limitations can severely hinder your ability to scale beyond a certain point. So if you have a brand new account on AWS, you have limitations on the amount of functions that you can run simultaneously. You may not be able to run more than 5,000 depending upon what your service configuration level is. There are other limitations for other items like SES for being able to send emails. Initially, everything is going to start in a sandbox mode. You may have to take that out of sandbox mode to actually send an email to somebody. So there are issues with individual cloud providers that you may have to overcome to get your application into production. And one thing to note if you're on AWS, and this may exist on Google as well, if you're deploying multiple production applications to a single account, that can cause big problems. Don't do it. You will run into resource and log naming problems, aggregated billing reports, so you can't tell how much each service costs, and you may have interlaced network problems causing congestion between your services. One thing you can do to bypass that is use organizations. Organizations give you accounts within accounts on your cloud provider, which allows you to completely encapsulate your entire stack. You can also do that for environments as well. So if you want to have 10 different environments for a particular customer, just make an organization for those environments, and each one of them will be completely isolated from each other. They're easy to scale. You now know the billing for every single stack individually. You can also detail down to the function level what the bills are. And you have no problems with network congestion because every single one of them is running on its own. Other issues within the framework itself, there are some logic concerns that you have to deal with when you're designing a serverless architecture, and one of those is spin-up time. Spin-up time is something that's a systemic problem in serverless frameworks where you're running in an on-demand container. You're not running in a standing server. So how does an on-demand container work? Well, your code is actually going to sit in an S3 bucket somewhere. When somebody is running your code is going to get pushed out to an on-demand container, which is a server somewhere. And you have to transfer those files from a bucket off to that container, and it has to start running, executing your request, and returning you a result. Well, if you have spin-up time, which these all do, spin-up time is the time it takes for your code to actually execute. That includes the transfer time to go from the storage location to the execution container. So if you have a large application, it's going to take a while to move it to the container. If you have startup procedures, it's going to take time for that to happen too. So to bypass that or to mitigate these issues, keep your functions small. Single domains of concern. Do not try and have functions do more than one thing, because if you do, your code size is going to increase and your spin-up time is going to increase accordingly. So keep things small, spin-up time becomes negligible. Another thing, serverless is not designed to handle CPU-intensive tasks. Do not try and mine bitcoins with this. You will lose money. In fact, you will lose thousands of dollars.
You can do it in multiple function executions.
You can, but that's not part of this. You generally want to stay away from CPU-intensive tasks in a serverless architecture if you're staying true to the original intentions. So keep functions small, don't try and do heavy processing.
So knowing that you need to keep the functions small, what if the nature of your application is you've got some functions out there that have a lot of business rules to them, there's a lot of complexity to them. You can't make them any smaller than they are. because of the business requirements?
It really depends, though. It depends upon what your architecture is. So if you're splitting up your functions, functions can trigger functions, which can trigger functions. So there's an infinite level of dependency that you can just chain logic to logic to logic to logic. So if you're separating concerns, yeah, we're getting to that. So there's, I actually could have probably expanded upon that, or is it may be coming up. Okay, so a small example of that here is we're actually doing some basic chaining in this example. So if a user comes in and hits API Gateway, they want to create a new user account. They're going to do a post call. That's going to insert a record into a database. Instead of just doing a manual event and this one triggering this one directly, we can actually use a DynamoDB trigger, or you can do it in other ways too if you're running different database stacks. You can set triggers on your database layers to actually trigger further functions. So if you separate your concern into smaller functions, you have functions triggering functions. Your logic is dependent upon a chain of logic that came before it, which allows you to keep the complexity, but you're reducing the size of each individual function along the way. Does that make a little more sense? I probably could have had a better diagram for that, but if we want to have the post here, we're going to create a database record at the end of this function. That'll trigger our welcome email function. Well, we can also trigger other things off of that. Go ahead and chain another one that says as soon as the email is sent off and we have confirmation of that, go ahead and email our administrator and let them know that that was sent off. Go ahead and trigger another function to go ahead and update records in the database for creating preliminary records for that user for other things like status containers or message containers or workflows. So you can chain an almost infinite amount of logic behind it.
So how would you indicate that even the diagram you have here where two things are going in parallel, or if it's a chain scenario, what if the second step fails? How would you roll back step number one?
Well, that is something that you have to design into your workflows themselves. So you can't necessarily say that if one function fails, it's automatically going to roll back the previous function's execution. But what you can do is on each execution of any of these, you can trigger subsequent functions based on the success or failure status of the function that just ran. So if you're going to say I'm going to have a rollback operation, your rollback operation is a function in and of itself, which would trigger off of the error case of the previous function that just ran. So you end up having a very linear workflow.
What the previous state was.
States can pass through them. So if you're chaining, it's all event driven. So
What I'm saying is you would need to know what was the state before step one that I need to roll back.
yeah, you can pass all that along in the event chain.
Okay.
So you can pass along whatever you want from event to event to event. Each of those functions can pull data from the previous one through the event model. So it's a little bit awkward in the paradigm. It makes things a little more obfuscated. Everything you're doing is intended to be either single operation or chained operations. So there's no, we're going to do complex logic in one function call that's going to do a database record here, it's going to modify another record over there, it's going to move something in the file system here, and it's going to send an email off there. All of those would be separate functions that are chained off of each other. Make a little more sense?
If you guys, sorry,
So,
anybody
let's
wants
see.
to come grab a sample?
Yeah, serverless scaling configs. Once you're using serverless scaling, you can scale up nearly infinitely with minimal effort. There's almost nothing required for you to accomplish 1,000 users to 100,000 users to 1,000,000 users. Very little effort whatsoever. Really, the biggest thing is just designing your logic to not fail as you scale. The services that are running your logic won't fail. When you're not running, you're not paying for anything. All right, so we're going to wrap it up here. There's not a whole lot left content-wise, and I've got a very short demo of an actual deployment and a basic test of a system. So benefits of practice, I think we just discussed what some simple needs were going to be from a particular implementation. If we want to add authentication to our API, we can do that through API keys, which would be auto-generated during the deployment phase. You can link that with Cognito so that you can do user management. You can create user accounts in a managed environment where you don't have to maintain those records yourself. Those records can be cross-checked against API calls themselves to limit access to particular calls. So it allows you a lot of flexibility in how your user management is interacting with your API to give you greater security. If you're using a database layer like DynamoDB, where you can use JSON, you can use all kinds of nested models, giving you a lot of flexibility in the data that you're storing and how you're storing it. You can use CloudWatch triggers with cron-style syntax to execute functionality on a schedule. You can also do event-based, based on rules. So if a database record gets created, you can trigger a workflow. Database record gets deleted, you can trigger a workflow. One gets updated, trigger a different workflow. So you have a lot of functionality that you can trigger off of all kinds of events, allowing you to separate all your concerns and all your workflows. Exit code 0. So we're done with that portion. Now what we're going to do is show a very basic example of what this looks like. This is a very simple serverless architecture that was actually pretty much nearly identical to the one that we deployed for a customer fairly recently. In this, I won't go through all the configuration options right now, but this one file is actually defining my stack. So I don't have to worry about particular server implementations. The server implementation is handled during deployment phase. I'm creating encryption keys for hiding all of my environment variables, role assignments for the services that are actually executing in between. Roles for all of my Lambda functions to execute appropriately and use the services they need. SNS topics to receive event data when something goes wrong. Dead letter queues for when functions actually do fail. We need somewhere for them to go. Buckets for data storage and data exports. Database tables in our document storage system that are both maintaining records and triggering extra functionality, with basic scaling policies applied. And our functions themselves, and this is the fun part, is this right here is the entire functionality definition for the app. And that's about maybe 100 lines of code. That defines my server, API routing, what functions are getting executed, whether it's encrypted or not, whether it's a private function or not, whether there's authentication required, and parameters that get passed along the way. Very, very easy to do. And we'll go ahead and do a test run and see what happens.
While that's deploying, can you show them a function?
Yeah, I'm about to. So in a simple implementation of a function here, what we're trying to do is, yet again, just reduce concerns. So I've got some endpoints defined that my configurations are pointing to. So visitor update, we're going to update a particular visitor record. This is the logic for that entire API call.
Make the font bigger.
There you go.
A little better?
Awesome.
Thank you.
So this is the entire logic path for that API call from start to finish. It's incredibly simple. There's a lot less code than you would traditionally see in a large stack. And it does everything we need to do. We're verifying input, mapping input to our targets, updating records, reading them back out, building responses, returning that back to the client, or dealing with error responses as needed.
So if you're using Node and you need to load extra NPM packages, how do you tell that to the server? I mean, is there like a configuration thing that
Yes, there is. So if your package JSON, the standard stuff, you're going to go ahead and load packages in here. And in your serverless config, you don't have to do this, but I always define custom package definitions. I'm only including things that I need for whatever functions I'm deploying. So I exclude other packages that may be a transitive dependency. So dependencies of dependencies, if they're not needed, I'm not going to include it. So I'm reducing my package weight, which speeds up or reduces my spin up time and speeds up deployment and execution.
So,
As your functions and all the function kits, okay, what type of visual function mapper software would you recommend using to keep track of which functions you have across the application?
Well, there's a couple different ways you can do that. Since all of this, in this particular instance, all this is being used on AWS, but also works in Google Cloud and a couple other providers as well. I generally tend to stick with the AWS specific stuff. So if I need to figure out which functions I have, I'll go to Lambda directly and see my function list. If I need to figure out my API calls, I'll go to API Gateway and see my entire API definition really quickly. If I need to deal with logs on any of those, CloudWatch contains all of my logs for both API Gateway and my individual functions. Let's see, if you want to do just like a strict visualization, one option is to go with, so if I can pull it up, CloudFormation itself has a nifty little template where you can use their designer tool, which is a visual tool for dealing with stacks. You can load that from serverless. So you can see what your stack is going to look like visually, and I'll show you what this implementation looks like. It's a lot more complicated though when you look at the visualization. So there's little things that are happening behind the scenes that you don't have to worry about in serverless, like how am I routing API calls to API Gateway? How am I mapping the input from that API call to an event that then gets passed to a proxy that then goes to your function call? So there's little things in the way that you'll see in the designer that you normally wouldn't have to deal with. Let's see if we can get that going.
Can you share that code Tim, after the session?
Say again?
Can you share the code?
Oh yeah, well,
Oh, right now. Right here.
that is the code.
I mean, well, the whole set.
Yeah, I mean, there's more to it. I've got some model definitions and response template management and things like that. Those are all just custom written based on the needs for this particular application. The biggest thing is what you care about is your handler here. Your handler is the only thing that is exposed outside of your function. So it calls that, all your logic needs to be self-contained within that one execution, whatever you need. So since we have our stack created now, I'll show you what that looks like in AWS's design tool. There's a little more than what I have to find in the serverless config. So this is the stack. There's a lot of things going on. I have, I think, 6 API calls defined right now, and there's a lot of things going on behind the scenes to get them all to work together.
I mean, that's like API Gateway, Dynamo, like everything, right?
Yeah, this is showing your event handling, your routing, event mapping, log management, and role management, all kinds of things. So if we look at our API definitions themselves, this is the entire API. There's not a whole lot to it. All this stuff behind the scenes is getting events to go to the right place at the right time with the right roles.
So in this code over here, does each
Oh, the code?
yeah. So does each JavaScript file correspond to a specific function in this example?
It doesn't have to, but for separation of concern, it's generally best to not use object-oriented practices at the topmost level, which sounds counterintuitive, but what that does is make sure your topmost level is functional style programming. Everything that utilizes is object-oriented though. So the top level being more traditional functional style programming allows you to keep everything lightweight. You're not going to be loading in things that you don't need into your function, which if you're packaging individually, again, is going to speed up your execution time and reduce spin out. So
Can you talk a little bit about the packaging? So can you go back to your serverless config?
the config, yeah.
So you've got all these predefined packages in here, but then how do you separate out, like it's going to bundle up that function for you, right, when it deploys it out. So it's going to pull all these packages into the functions that are using those. So is serverless only going to package up what's in the require statements for that handler, or
Sort of. I generally don't trust it yet. They're still working on automated dependency management, so it's not perfect yet. Generally, I will manually include things that I need and manually exclude things that I need when I'm doing packaging, just so that I make sure I'm not including things that don't need to be included.
so? But you're still, when it creates that Lambda function, it deploys it out, and it's all bundled up.
Yeah, it's
Okay.
all bundled.
It's all bundled up. So, but then you're going to end up pulling in dependencies into functions that don't necessarily require those dependencies. Like you're bundling everything.
Transitive dependencies.
Yeah, you're bundling everything up into every function. right?
Yes, you are, but you can package each function individually.
Okay.
So if you package each function individually, you can reduce scope on dependencies to just what's needed for that particular function.
Where do you do that right now?
I don't have that defined in here,
Okay.
but all you have to do is add a package and include and exclude statements inside your function definitions.
Gotcha. Okay.
And then add one flag at the top for your service that says package individual.
Okay.
And then each individual one will get its own separate package. Each of those will be deployed separately.
Okay.
They'll all get run by the stack itself, but they'll all have whatever dependencies or you have specifically included for that
Okay.
function.
Very good.
So our deployment took maybe a minute and a half. We deployed all those API calls. We set up a database. We have all of our routing done. We set up a couple buckets in S3, and we should actually be able to test this. So if I go to my API call and I export what I have, we should be able to open that in Postman and actually execute an API call and see our database record pop up, and we should also get an email. So let's go ahead and create a user record here. We will need to double check our deployment to pull our API key. API keys are created during the deployment phase. Now these are not, the API key will stay the same unless you tell it to change on every deployment. So generally you want it to stay the same. So we'll add our API key into our header. We'll go ahead and create our body.
Can you add a front end piece
For what?
for the code? Is it, or is it
Well,
mostly?
you certainly can. I mean, serverless really isn't designed to deal with front ends directly. It's designed to primarily be a back end service.
Okay.
But you can run front ends off of these APIs. So in the H3 project, the entire thing was a front end iOS application, but the entire back end was running in serverless.
Okay.
So we were able to go ahead and test our API call that we just deployed. This deployment didn't exist until we ran it 5 minutes ago. So brand new stack, we're already having records created. We can go check that in our database layer and make sure that the record actually does exist, which it does. And we should have received an email, which we just did. So it's very, very easy for you to package up functionality and workflows that chain off of each other, incredibly simple to deploy, easy to configure, easy to manage, and you're going to save a lot of time and money doing this. And one thing I would definitely encourage all of you to do is try it, play with it. It costs you almost nothing to get started on this. For the H3 project that we ran, just to get the thing off the ground and running for an entire month cost $6. So, dirt cheap. It'll cost you more than that to run a microserver for a day.
So, in this example, how many cloud functions do you have on the lambda applications?
I'm sorry, say that again?
So in the example that you just showed us, the deployment, how many lambda functions do you have? Is it just one? Or?
Oh, no. We've got multiple Lambda functions, and they can be chained at different areas or executed through different events, and not all of them are even public. So we'll pull some of these up real quick. Go ahead.
So if I have two lambda functions that need to make database connection, does it mean both of them have their own specific config file, or how does it work?
Well, what I would do, and this is sort of part of the Lambda paradigm itself, not necessarily serverless, is you really want to pass references like that across through environment variables to your functions so that you have one source of configuration and it deploys out to any functions that require it. So in the serverless architecture, and this translates out to Lambda in an AWS deployment specifically, at the top of my config file, I have all kinds of custom config options. These are all options that I made myself that I can reuse throughout the system as environment variables. So if I want to pass along references for dead letter queues or database connections, I can pass all of that along through variables that are encrypted during the transport level, and only once they're executing in a function container is that decrypted, and I can now use that, a connection string or a password to a database or whatever. So that's the easiest way. There's other ways to do it too, but that is by far the easiest way to config once, deploy multiple times.
What about for secure credentials and stuff that you're putting in environment variables? Because you don't want to put them in your config, right?
You do and you don't.
Okay.
You don't want this to go into Git. So I will say that your serverless config can go into Git, but if you have secure credentials, you don't want to put those into Git. A way around that is you can use a password file and import that into your serverless deployment during the deployment phase, which will get passed along as environment variables, and leave that as an encrypted file when you're doing commits. So there's no way anybody can read it as plain text anyways. When it's going through as environment variable, there's multiple levels of encryption happening on the AWS side, where your environment variables are always encrypted at rest. So nobody can read them except for, well, actually, even the function can't read it when it's at rest. When it's being deployed out to the container, you can use a KMS encryption key manually to add encryption during transport. So only once it's executing on a container is it ever decrypted, and the only person that has access to that is the function call itself, in which case you bypass your security.
So, but you have to set up KMS separately from...
Yes and no. So you can actually do KMS inside of here in your resource definition. So I have a KMS encryption key that I defined here in my resources that automatically gets applied to my functions. And that's going to be for the transport portion. So the rest is done for you. You don't have to do encryption at rest. It's automatic.
Okay.
But the encryption during transport, I have a manual key definition here with a role associated. That gets applied for the transport portion of those variables. And then once they're on the function container, it's fine.
Okay, cool.
So even security variables, you can still use this kind of workflow to config once, deploy multiple times. And for the functions, we deployed, was it 10 functions here? And only a handful of these are even available through the API gateway. So not all of these are actually API calls. We're intermixing functions, not API layers and back-end triggers. You're worried about just functions. So some of these are going to come from an API. If we're talking a visitor add, visitor get, question get, all of these are going to be run through the API. But what about email contact request or email new visitor? These are triggered functions. So when I post that visitor record, it creates a new user for me. It automatically creates a trigger on the database layer that says, hey, you need to email this guy. So as soon as that record's created, that data gets passed as an event to the email function. The email function now does its piece. And if we want to keep chaining more triggers on, we can. We can chain as many as we want. We can also go in parallel. So if I needed 3 triggers that execute in parallel off of that one database record insertion, I can. So it makes it very, very easy for you to just mix and match functionality based on what you need, not what your systems are limiting you to. Any other questions?
So, in your ideal world, would there ever be a situation where you would prefer to go back to more traditional architecture, or do you feel like this can almost always replace the traditional architecture? It's like better in every way.
The answer to that is yo. Yes and no.
Okay.
It really depends on what you're doing. So there are certain things that serverless is really not designed to do, but it doesn't mean that you can't intermix serverless with traditional architectures. So if you have, and this is an example I brought up just a moment ago, if you've got to deal with video streaming is an incredibly CPU intensive task. That's something you don't want serverless to do directly, but that doesn't mean that you can't intermix that with traditional architectures for media transcoders and things like that. So if a user is going to post a video, you're making your own version of YouTube, I'm going to submit a video that's 4K. Well, I need to also be able to stream that out in 6 different resolutions to anybody that's going to view that downstream. I'm going to submit through serverless. When that happens, that's going to trigger my media transcoder service, which is outside of serverless, but that's an AWS internal service. Google has their own competing version of that. You're going to trigger that CPU intensive task to create the different versions of the video. Those are going to go into S3 buckets. After that happens, you're going to trigger another function that's going to update a record for that in your database, which now makes it visible to other users in your system. And the next person who pings the system and says, hey, show me what videos are available, now has multiple options for, you want to see it in 480, I want to see it in 720, I want to see it in 1080 or 4K. But you're intermixing serverless with traditional architectures based on your concern.
Well, but
4%.
but when you say that though, those are still, you can still set up all those services through serverless, right? Like you can.
Yeah, yes and no. Like the transcoding service is a hosted service, but you could write your own. So if you want to make a custom one from scratch,
Sure.
you can do that. Just make an AMI and include that in your resource definition. You can deploy it with the stack.
Right. So then I think closer to what your question was is, what about Lambda versus EC2? Like when would you want to choose writing everything as a Lambda function and hosting the API through API Gateway versus running an EC2 instance and just using Express and Node?
I would say probably the only major benefit of running a traditional architecture over serverless is no spin-up time. So if you have to have incredibly high performance, meaning I need zero wait time whatsoever, it's better to go with the traditional route. However, separate out your concerns again. What functions do you need to run with that type of performance? Can you limit that just to a very small subset of your total functionality and then put the rest of it on serverless? Most of the time you can. If you need like authentication services, if you have to have that be super performant, that's fine. Run a dedicated stack for that integrates with your serverless architecture for all the other services that you need.
So for spin-up time, are we talking about milliseconds or are we talking about seconds? So for
Usually
example-
milliseconds, but it really depends upon what you did with your package. So the larger your package is, the more spin-up time you're going to have because that's going to increase your transit time from your code storage to your code execution container. So if you can keep your package under 5 meg, it's going to be like maybe 100 milliseconds, 200 milliseconds for spin-up time. And that's going to last for usually around 5 minutes. You'll have access to that container. It depends upon what AWS's load is right now in your region. So your container could die in a minute and a half. It could die 5 seconds after your function's done. But generally speaking, if you're running constantly, you're going to keep at least one container alive.
So what about running an entire site, like the front end on serverless architecture?
Yeah, it's not a problem. You can certainly do it. Just make sure you're running things in an asynchronous manner. So I would write your front end where your front end is dependent synchronously on data coming from an API. Write it where it's asynchronous. So things, the UI loads and then API calls happen and then that comes back and affects the UI. Not the UI doesn't load until an API call finishes.
So now you say that. So say for example we have a function that invokes some method and it just has a callback. How does the process, atomic process knows when the doorman goes off the cache, but like not, you don't get billed anymore, even though you're going to have a callback. So it's not really doing any code, it's just waiting for someone to call you back. How does that work?
You're sort of referring to running asynchronous processes within one of the serverless functions.
Right.
If your function is waiting on something to happen, then you're paying for it. So every second that your function container is executing code, including waiting for something to happen from an external service, you're paying for that. So really you have to design smaller functions to get around that problem. So if you have to run asynchronous database updates, that's fine, but only run one. Don't run 3 updates at the same time. Run one and then chain the next one and then chain the next one and have each of those run as small of a time frame as it possibly can until it gets to the next phase. Don't have one function run multiple things back to back to back.
I have one more question.
Mm-hmm.
So about the eventing, about that chaining. So is that a separate AWS service or is that built within Lambda to send events out?
It is technically a separate AWS service. It's CloudWatch is
Okay.
what you're using for your rules engine.
Okay.
But that's baked into the core of serverless because all cloud providers have their own version of that.
Yep.
And that's really just governing event handlers on services that are internal to that provider. So if we're using DynamoDB on AWS, it has 50 some odd different types of events we can trigger off of. All that's going through CloudWatch. Serverless already knows how to set up CloudWatch appropriately based on what triggers it has available. Same thing's true for Google Cloud, even though the naming conventions are a little different. Anything else?
So
Not all events are available, right?
Hmm?
Not all the events are available for Lambda functions. Is that correct?
Not all of them technically, but an incredibly large amount of them are.
They keep adding more each.
Yeah, they add new ones probably every month right now. And the ones that you have access to in your serverless config are the ones that they already supported, but it doesn't mean you can't support other ones on your own. So if you if you have a resource definition for a CloudWatch rule, that supersedes anything that you have in your serverless definition anyways. So you can add your own custom rule definitions all you want.
There are a lot of serverless YAML files available that demonstrate some working with these events, creating functions.
Yeah, there's a ton.
Any good resources that you recommend for those YAML?
Yeah, I mean, I would start off, the best place to go initially is to go to the serverless documentation website and go to their AWS serverless.yaml file, the one that has all the possible options. Now, that does not include custom resource definitions outside of what serverless currently supports. So anything you can define in CloudFormation on AWS, you can put in your serverless config in the resource section, and serverless doesn't even have to support it for you to be able to deploy it as part of your stack. But for what serverless does support, yeah, you're kind of limited on what they have available in that document. I can add in some links though. Before I post the slide share, I can add some links. You guys. Sounds good. Thank you. Mm-hmm. Anything else?
This may be a stupid question, because I've been away from technology for a while, but it feels like the more granular you make the functions, do you run the risk of the trade-off of having a chatty application, like from the database perspective, you know what I'm talking about?
Yeah, you're talking about having too many connections back and forth. Is it possible? Certainly. But that's a design concern that you can mitigate up front if you limit your workflows. So limiting functions is one thing, but limiting workflows is another. How many times do I actually have to talk to a database in a particular workflow? If I'm creating a database record and triggering off an email and triggering off an image upload or a resize and putting stuff into a storage bucket, how many times do I really need to talk to the database in that workflow? So rethinking your design patterns is going to limit that. That's how you mitigate. Any other questions? Nope. All right.